Ever wonder how the internet actually avoids gridlock? I mean, think about it. Every single second, billions of devices are just blasting data back and forth. You'd think with all that traffic flying around, the entire system would just completely lock up. But, mostly it doesn't. And the reason why is this absolutely fascinating piece of invisible engineering. Welcome to this explainer. Today, we're decoding the invisible master traffic controller of the internet, TCP Congestion Control and the AIMD algorithm. This is the underlying math dictating exactly how fast your data can travel. It's the unsung hero working behind the scenes on practically every connection you make, keeping our digital world spinning. Here is our roadmap. We'll look at the digital traffic jam, meet the AIMD algorithm, break down the 2 rules of traffic, see AIMD in action, and finally visualize the Sawtooth pattern. Let's get right into it.
Section 1, the digital traffic jam and the stakes of data transmission.
Okay, so we got to start with the core problem this algorithm was actually built to solve. Packet loss basically equals network congestion. When senders push data out too aggressively, the network just can't handle the sheer volume, and individual packets of data get lost in the shuffle. The network usually figures this out through timeouts, like a response just took way too long, or by getting multiple duplicate acknowledgments. When that happens, the system assumes a collision has occurred. It's literally the digital equivalent of a massive highway pileup. Section 2. Meet the AIMD algorithm, the master traffic controller. To prevent those catastrophic collisions, TCP relies on a highly responsive system, AIMD. Let's break that acronym down. It stands for Additive Increase, Multiplicative Decrease. It represents this perfect calculated balance between pushing for maximum speed and immediately applying the safety brakes to avoid a crash. It's not a static speed limit, it's a dynamic, living equation constantly testing the waters. Section 3. The 2 rules of traffic. Increase versus decrease. The whole algorithm runs on 2 totally opposing rules for adjusting what we call the congestion window, or cwnd. On one side, you have additive increase, creeping the speed up step by step when the road looks clear. On the other side, multiplicative decrease, just slamming on the brakes when a crash is detected. Let's look at how each of these works independently. Great. Rule 1, additive increase. During a phase known as congestion avoidance, TCP slowly tests the network's capacity. When there are 0 packet drops during a full round-trip time, an RTT, the sender gets rewarded. Since the acknowledgement came back cleanly, the sender safely adds exactly 1 additional segment to its speed limit. It's steady, linear, and super cautious. But the absolute second a speed bump is hit and a packet is lost, triggering those timeouts we talked about earlier, the algorithm shifts immediately to Rule 2, Multiplicative Decrease. It assumes the network is congested and ruthlessly cuts its sending rate in half. It doesn't drop by 1, it cuts the entire congestion window by 50%. This severe reduction is absolutely crucial to instantly alleviate potential gridlock. Section 4, AIMD in action. From 0 to gridlock. Now, before that cautious additive increase phase even kicks in, a connection goes through what's called slow start. Honestly, slow is kind of misleading because it actually grows exponentially. Imagine our initial congestion window starts at just 2. If both segments make it back, the window doubles to 4, then to 8, and so on. The algorithm is aggressively hunting for the network's absolute ceiling. But here's the kicker. That aggressive exponential doubling stops the exact second a congestion event happens. Bam! A packet is lost, and the algorithm forces a massive 50% drop in the transmission window. No questions asked. So, after slashing that speed limit, say dropping the window from 8 down to 4, the slow start phase is officially over. The algorithm now shifts into congestion avoidance. From this new, much lower baseline, it switches back to Rule 1, cautiously adding just 1 single segment per successful round trip. Section 5, the Sawtooth pattern. Visualizing the network cycle. When you actually plot all these mechanics on a graph over time, it looks wild. The algorithm gets locked in this constant loop, aggressively climbing, suddenly dropping by half the second it hits a limit, and then cautiously, linearly climbing again. The data literally visualizes as the jagged teeth of a saw. Those sharp peaks are the moments right before congestion, and the steep cliffs, those are the multiplicative decreases. To quickly review the whole life cycle, we start with slow start's exponential growth. Then, inevitably, we hit a congestion event where a packet is dropped. That triggers the multiplicative decrease, instantly halving the window. Next, we enter congestion avoidance with its linear +1 growth. And finally, the cycle just repeats. It's this continuous self-correcting loop that lets TCP fully utilize network resources without taking the whole system down. Which brings us to a really great takeaway from the source material: a good balance between aggressive sending and conservative throttling. That basically hits the nail on the head for AIMD. It's an elegant, mathematical push and pull. By pushing hard when it can and getting super conservative when it has to, it keeps your data flowing efficiently. But as we wrap up this explainer, I want to leave you with a kind of fascinating final thought to ponder. If AIMD literally relies on experiencing packet loss, essentially a digital crash, just to figure out where the speed limit is an algorithm that requires occasional failure to function truly the most efficient way to manage the massive, complex future of our internet? It's definitely something to chew on the next time you're streaming a movie or loading a web page. Thanks for hanging out, and keep exploring the incredible mechanics of our digital infrastructure.